I can. Welcome to the seminar series on modern artificial intelligence at the NYU Canton School of Engineering, where we are bringing together faculty, students, and researchers to discuss the most important trends in the world of AI. These talks are being viewed by people around the globe via live streaming, and we are thrilled to help spread the word about the amazing work going on in the AI community. I'd like to thank Dean Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering, for supporting the series and graciously hosting our esteemed speakers, all of whom are world-renowned experts whose research is making an immense impact on the development of new machine learning techniques and technologies. Our guest today is Karl Friston, who serves as the Principal Research Fellow and Scientific Director at the Wellcome Trust Centre for Neuroimaging at University College London and a professor at the school's Institute of Neurology, as well as an honorary consultant at the National Hospital for Neurology and Neurosurgery. He has been called the genius neuroscientist who might hold the key to true AI. An authority on brain imaging, he earned that description with his invention of statistical parametric mapping, a computational technique that allows for more accurate comparisons of activity within different crania, as well as his development of an imaging technique known as voxel-based morphometry, which you may have read about in a connection with a now famous study of London cab drivers. He's also responsible for dynamic causal modeling, a framework that has proven exceptionally useful to neuroscientists. His mathematical contributions include variational Laplacian procedures and generalized filtering for hierarchical Bayesian model inversion. And his main contribution to theoretical neurobiology is a free energy principle for action and perception. Educated at Cambridge University and King's College London, he also holds honorary doctorates from the University of Zurich, Radboud University, and the University of York. We would be here for much longer than we actually have if I listed all his other honors, but I'll just mention the first Young Investigators Award in Human Brain Mapping, the Minerva Golden Brain Award, a College de France Medal, a Weldon Memorial Prize and Medal, the Charles Branch Award for Unparalleled Breakthroughs in Brain Research, and the Glass Brain Award, a Lifetime Achievement Award in the field of human brain mapping. Karl is a Fellow of the Academy of Medical Sciences, the Academia Europaea, and both the Royal Society and the Royal Society of Biology, as well as a member of EMBO, an organization dedicated to excellence in the life sciences. And I hope that I won't embarrass him by mentioning that he has an age index nearly twice that of Albert Einstein. He's currently working on models of functional integration in the human brain and the principles that underlie neuronal interactions. I'm excited that he will be speaking to us today about deep inference and exploring the fascinating question of whether there is an underlying information theoretic imperative that renders perceptual inference and decision-making two sides of the same coin. Without further ado, let's give him our attention. Karl, the stage is yours.
Thank you very much for that lovely introduction. That was a very complete. That was more than was in my CV. That's very impressive. I have to say, you've mentioned every prize I've ever got. So that's not just a selection.
I'm very glad.
I should also say that I've just spent the past hour talking to the students, and I think I've said everything that I know, but now I shall try to reprise some of the key points over the next few minutes. So I'm going to be talking about deep inference, by which I mean really all the issues that attend self-organization, sentient behavior, that can be formalized in terms of a normative or an optimization-like procedure. And I'm going to be talking about the imperatives for sentient behavior in terms of self-evidencing. And I'll try and explain what I mean by self-evidencing by reference to normative models and motivate the particular optimization function that's going to be an evidence lower bound or variation free energy from the perspective of those people who might be working in machine learning and artificial intelligence. And then I'm going to go through some very simple worked examples just to evince the basic mechanics of the belief updating and inactive aspects that follow from this treatment, with a special focus on gathering data in the service of looking for evidence for my own existence, hence this rather poetic title from philosophy, in fact, of self-evidencing. So I'm going to conclude with a brief simulation of inference under deep generative models that have a sort of separation of temporal scales that one can think of as a metaphor for the way that we make sense of written or heard language. So self-evidencing, I'm going to assume at the beginning that we can understand everything in terms of the behavior and the internal belief updating of a sentient agent, namely perception and action, as an optimization process, an extremization process, and the quantity that I'm assuming this maximization applies to is simply the probability of exchanges with one's world or observable outcomes, given the kind of model that we have in mind, or given me, for example. And I'm doing that, or I'm expressing it in that way, just to make a connection with many frameworks with which you will be very familiar from one perspective or the other. So, for example, if you're in psychology or engineering, you can think of the log of the probability of the kinds of outcomes that I would expect to encounter if I was me, as scoring the attractiveness or the value of those outcomes or states of being that characterize me. And we'll see later that this is lower bounded by this variational free energy, a function of observations and some sufficient statistics about the causes of those observations. So if I read this log probability as value, then we can sort of shake hands with things like reinforcement learning, optimal control theory in engineering, and if I was an economist, expected utility theory. An alternative perspective is afforded by information theory. So the negative of this quantity is known in information theory as self-information, surprisal, or more simply surprise. So it's just the implausibility of something like me encountering these outcomes or observations. And that perspective lends itself to an interpretation of the Inference principle, or the principle of maximum mutual information transfer, closely related notions of maximum efficiency or minimum redundancy by Horace Barlow, for example, or indeed an explicit optimization or extremization of free energy in the free energy principle. That's nice because the average of surprise is entropy, which means that if I'm trying to maximize in the moment my value or minimize my surprise, I'm inherently trying to upper bound or minimize the entropy of my exchanges with the lived world. And that, of course, is the holy grail of self-organization in cybernetics, in physics. This would be known as synergetics of the Hermann Haken sort, with a special focus on the separation of temporal scales. And if there's a physiologist, it's just a statement of homeostasis, keeping the variables that matter within bounds to offset or counter or bound their dissipation and dispersion into non-viable regimes. There is a final interpretation of this quantity that I'm going to leverage here, which is that a statistician would take on this quantity. He would understand this as a probability of some observed data under a model that generated those data. And this would then be the marginal likelihood or the model evidence. So this just says that I am in the game of maximizing the evidence for my model of the world. And from that, we can understand the motivation behind things like the Bayesian brain hypothesis, evidence accumulation, in its various flavors, including predictive coding. So that's where I'm starting. So let me just drill down on this evidence bound, this variational free energy, and see why it is such a useful construct from the perspective of artificial intelligence, particularly, but also statistics. For those of you doing deep learning with variational autoencoders, this is just the elbow or the evidence lower bound, and can always be written as a functional of a effectively a generative model, or beliefs about the relationship between the consequences, observable consequences of some latent states S at a particular time, that is used to optimize my beliefs Q about the hidden or the latent states. So here I've expressed the free energy that can be thought of as a proxy for the evidence or the marginal likelihood as a negative entropy, negative energy and the entropy. And I've done that just to sort of highlight the connection with James's maximum entropy principle, that the best beliefs about something subject to constraints are those which leave your options open and maximize the entropy of those beliefs. So what are the constraints? They're usually articulated in terms of a generative model that comprises a likelihood and a prior, the probability of some outcomes given their causes, and my prior beliefs about the plausibility of those causes. This deconstruction, or this way of writing down the objective function behind self-evidencing, lends itself to an interpretation which provides a clear motivation for why you might want to use this kind of objective function in artificial intelligence research. So, for example, I've written it in a form here that licenses its interpretation as an evidence bound in term. So I'm expressing the free energy here as an expected log evidence plus a KL divergence, which can never be less than 0, hence a lower bound, where the log evidence, because it's predicated on a generative model, necessarily endows any belief with an explainability in reference to that generative model. So that provides for free sort of transparent prior assumptions, all sorts of technical benefits in terms of hyperparameter optimization and the like. What we will see later is it also affords another kind of optimality, another kind of Bayesian optimality that is normally associated with the principles of optimal Bayesian design, basically getting the right kind of data to resolve uncertainty about how you think those data were generated. That's in itself important if you're designing machines or artifacts that need to be smart in relation to the kind of data that they operate in and that they select to induce their belief updating of the problems of the sort you will get in data foraging and epistemics, and presumably in artificial general intelligence. I've rewritten this expression here in a slightly different way, just by swapping around a couple of terms to express it in a form that a statistician will be more comfortable understanding it, basically as a mixture of accuracy and complexity. So the accuracy is just the expected log likelihood of my data or observations under some beliefs about how they were caused, the latent states, that is supplemented by a complexity cost. And that is just the divergence, the KL divergence between my prior beliefs and my posterior beliefs, having observed the data. So it literally scores the degree to which I've changed my mind after I've seen some data. And of course, the greater degrees of freedom that I'm using up in changing my mind, the greater the complexity cost. And this underwrites, or is a formal statement of Occam's principle, in the sense that we want to supply accurate explanations for our observations that are as minimally complex as possible, or as simple as possible. One can also read this from the point of view of engineering, in that this complexity cost is literally going to be a computational cost. It affords a description of rationality under computational cost constraints in terms of boundary rationality. We move from exact Bayesian inference to approximate Bayesian inference that allows us to express our models in terms of priors and simplifying heuristics that suppress or finesse that computational cost. And if you're a physicist or an electrical engineer, then via the Zielinski equality and Landauer's principle, that belief updating, that destruction of information that is necessary in order to change your mind, costs energy. So you can measure the computational cost just in terms of either metabolic cost or the amount of electricity that you're using up in doing your processing. The real point of this talk, though, is to take that notion of self-evidencing and that particular focus on a variational free energy or an evidence lower bound. And that's what implications does that have when I am in charge of gathering the data? Basically, what are the imperatives that emerge when thinking about the consequences of action in terms of the evidence bound or the free energy that would ensue after I have made an act? And of course, we don't at this point have the outcomes of that action. So we have to take an expectation, technically under the posterior predictive density, over the outcomes, if I did that. And the story I want to tell, so everything else is basically telling this story. The story is that when you take this expected free energy, the expected accuracy now becomes exactly the objective function that you'll find in optimal Bayesian design, basically designing the right experiment, the right acts, the right way of sampling the world that maximizes the information gain that can be regarded as the expected accuracy. In a very similar way, that computational complexity cost, when we take the expectation under some yet to be observed data, becomes exactly the objective function found in Bayesian decision theory, the Bayesian risk, essentially. And that these two, if you like, parts of the expected objective function are subsumed under an expected free energy that underwrites the optimal choice of behavior or decisions or choices or active sampling. So just to unpack that and motivate it in relation to objective functions and normative theories that you may be more familiar with, I usually start by asking the audience, imagine that you're an owl and that you're hungry. And then I ask usually the person in the front row, what are you going to do? And I won't embarrass anybody by doing that now, but normally I receive the very correct response, well, I'm going to search for food. I'm going to look for food. And the answer is absolutely right. And here's the bird of prey searching for its food. In that answer, there are some really key insights, key to deciding what kind of objective function you might look for in terms of trying to understand sentient behavior. So I am deliberately now going to introduce a dialectic between that state value functions of states and functionals or beliefs about states in order to compare and contrast. With the qualification, I'm going to put them back together again. But for the moment, let's just think about the standard way of doing this, that I could, if I were equipped with a value function of the states of the world that would ensue if I took this action U, then I could, in principle, work out the best thing to do from any given state, and that would be a state action policy. However, what we've just said is that the first thing that I'm going to do when faced with a real problem is search for the solution. But searching for the solution entails a resolution of uncertainty about the solution, in this instance, the location of the prey. But uncertainty is an attribute of a belief. And if you allow me to read belief as a probability distribution or a Bayesian belief, then what that tells you is that the right kind of objective function has to be a functional, not a function of states, but a function of beliefs about states. And I'm denoting that with G here. So really what we want to do is to take the actions that optimize my beliefs about states of the world. Furthermore, it matters whether I first search for the prey and then eat it, or whether I try to eat it and then look for it. So we have this added temporality here, and this that we're talking about sequential policy optimization, and we have to assess the path or the time integral of whatever objective function we choose to express it in the form of an action, a time integral of an energy function here. And the reason that I'm expressing it like that is that allows me to sort of compare and contrast two different sorts of principles that you might appeal to when trying to formally articulate sentient behavior. So on the one hand, if you believe that this is how behavior works, then you're implicitly subscribing to Bellman's optimality principle, and you will find this underneath optimal control theory, deep reinforcement learning, expected utility, Bayesian decision theory, and so on. On the other hand, if you think that you're trying to optimize a function of beliefs, then you're going to subscribe to Hamilton's principle of stationary action, or at least action. And examples here include the free energy principle. In neurorobotics, you'll come across things like intrinsic motivation, basically artificial curiosity that is there. It is in play simply to optimize our beliefs about something, essentially minimizing our uncertainty. We know how to make moves, sample the right kind of data. So we have baked into this principle of least action the principles of optimum Bayesian design that we can apply to sequential policy optimization, dealing with the kind of uncertainty that inherits from partially observed problems, such as partially observed Markov decision processes. So what is that G? Well, I'm going to sell the G as the expected free energy. And in so doing, induce this sort of computational architecture that can be understood or used to understand the action perception cycle. So the idea is very simply that you have some observable outcomes. You take these outcomes and you optimize, you update your Bayesian beliefs Q about what caused those outcomes, the hidden latent states, external states of the world beyond your sensory veil. And in so doing, you're going to maximize your evidence lower bound or your variational free energy. And we can regard that as perceptual inference. This now affords an optimal belief about hidden states of the world that I can then use to roll out into the future and evaluate the expected free energy that I would get if I pursued this particular sequence of actions or policy here. And then I simply associate the probability that I'm pursuing this policy with the expected free energy, which plays a role of a Gibbs potential, and then select the appropriate action from the selected policy. So this, in effect, provides the machinery for policy selection. I make that act on the world, I change the external states, they deliver a new outcome, and so the circle continues. So what I want to do now is just unpack the relationship between free energy and the expected free energy, using these notions of complexity and accuracy in a bit more detail. And again, what you will see is that this unpacking discloses things that you will already be quite familiar with. So what I've done here is just write out the expressions for free energy, variational free energy, and expected free energy that we've seen in previous slides, just to label these, just to license this particular labeling. So here's the expression that lends that would be appropriate to understanding this as an evidence lower bound. Here's the log evidence, and here's the KL divergence that makes it into a bound. Rearranging, just moving these two terms around, I get my accuracy and complexity. And the reason I've done that is to highlight this beautiful symmetry that you get under the expected free energy, which is just the expectation under the posterior beliefs about the things that I might encounter, observations, if I took this particular policy or decision pi here. And what happens is that expected complexity and accuracy become risk and ambiguity, and the expected KL divergence and log evidence become intrinsic and extrinsic value. So what do I mean by these things? Well, let's just first of all ignore extrinsic value and focus on this intrinsic value here. So what is this? Well, effectively, it's a KL divergence or an expected KL divergence between my beliefs about states of affairs out there, if I were able to see the outcomes consequent on a policy, relative to my beliefs without that. So in effect, it's the information gain afforded by that policy in terms of what I see or my observations consequent upon that policy. In the visual search literature, this is known as Bayesian surprise by people like Itty and Baldy. More generally, in the context of the principles of maximum efficiency, it's just the conditional mutual information between the causes, the states S, and the consequences, observable consequences in the future, given a particular policy or sequence of actions. So it's scoring technically the relative entropy, the information gain, the value of information that ensues from this particular policy. Sometimes, I repeat, known as intrinsic motivation in the robotics literature. Let's now take various bits of uncertainty off the table and see if we can get back to the objective function that would operate under Bellman's optimality principle. So what kinds of uncertainty can we take away? Well, the first kind of uncertainty we could remove is the uncertainty that inherits from systems that are only partially observed. So I'm now going to make the assumption that I can actually see everything in the world. So my outcomes, my observations, my sensors can measure exactly everything that matters. So the O's and the S's become the same thing. In other words, there is no ambiguity anymore about the state of affairs or the consequences of looking at those states of affairs with my observing observing apparatus. And then I'm left with this expression here, which is just a KL divergence between what I anticipate states of affairs or outcomes to be under the policy and my prior beliefs about the kind of states or outcomes I, as this kind of creature, would anticipate. So remember, these are the things that are attractive for me, that characterize me, and often in my world, they would be referred to as prior preferences. So this is just scoring the risk of diverging from my prior preferences under this policy. In engineering, it's known as KL control. In economics, it's known as risk-sensitive control. And it's simply a measure of the goodness of a policy measured in terms of the divergence from your prior preferences. And so finally, let's just take out another source of uncertainty, which is the uncertainty that accrues because of I don't know the consequences of my actions. So basically, I'm now taking the risk part or the intrinsic value part off the table just to reveal the extrinsic value here. And what is that? Well, it's just the expected utility from the first slide that I can read as an expected value. And this, of course, is synonymous with expected utility theory or expected value in reinforcement learning. So notice that in able to get from a sort of principle of least action to a Bellman optimality principle, what I've had to do is successively remove sources of uncertainty so that the belief-based aspect or the use of a functional beliefs becomes less important than just drilling down on the expected value as scored by my prior preferences. So what I'm saying here is that the Bellman optimality principle is a very beautiful thing, but it is a special case of a more general problem when you're operating under different kinds of uncertainty. Expressing that in another way, self-evidencing in terms of optimizing, in this instance, maximizing expected free energy, in my world known as active inference, just is the right mixture of maximizing the expected value and the information gain. That is just a reflection of two sides of the same Bayesian optimality coin, namely making the right kind of decisions, but also getting the right kind of data in order to minimize the uncertainty that enables me to make the right kinds of decisions. So I've just cartooned that in terms of expected value plus information gain equals expected free energy. So I'm going to conclude now with a couple of simple simulations to show you how this mechanics unpacks in practice. Starting off with a simple observation that in order to quantify the free energy, and in particular the free energy gradients that drive the belief updating, I have to have a generative model. So this is all about basically inversion, active inversion under a generative model. And the kind of models which we use to simulate sort of trials and behaviors of an experimental sort would be a Markov decision or partially observed Markov decision process that would be suitably explained or modeled in terms of this graphical model here, where we have states that generate outcomes through a likelihood mapping, usually denoted by a likelihood matrix or tensor here, A, and then the dynamics of the world are going to be encoded by probability transition matrices, B, that of course depend upon my behavior, the policy that in turn depends upon the expected free energy of that policy, G here. So that's the structure. These can be regarded as the priors, if you like, and this part of the likelihood of a generative model. Here are the equations that accompany this particular graphical model here. We can ignore them for the moment. The reason I'm writing this down as a graphical model is just to make an interesting point that if I can write down the probabilistic graphical model, if I can articulate the mechanics from the point of view of a generative model, then there always exists an accompanying factor graph, if you like, a conjugate of this kind of model in terms of message passing, where for those of you who are not familiar with factor graphs, basically the random variables, or at least their sufficient statistics, now map to edges, and the probability factors now become the modes. And the beauty of this, this kind of factor graph is that it immediately reveals the kind of message passing that would be implicit if I had this graphical model. So in other words, if I can write down a generative model, then I can always write down the factor graph. If I can write down the factor graph, I can always write down the message passing implicit in model inversion. And these are the messages that are passed amongst the various edges here, giving you a computational architecture that looks very much like what actually happens in the human brain, or indeed any brain. It's remarkably simple in the sense that, you know, we only have to infer a small number of unknowns. These are basically unknown states of affairs in the world, what I'm doing, my policies, and the model parameters that encode, in this instance, the initial states D, but more usually the likelihood mappings and the transition matrices A and B, respectively. And if one just takes off-the-shelf variational message passing derived from that factor graph, or organized in accordance with that factor graph, you get update equations that look very much like the kind of equations that people use to simulate neuronal dynamics and plasticity in the brain. So, for example, the expected states of the world under a given policy is just a nonlinear, say, voltage current activation function of some linear mixtures of, say, neuronal representations of outcomes and beliefs about the past and the future. Policy selection just becomes a standard softmax function of my expected free energy. Here I've just equipped this free energy with a temperature or precision parameter that itself can be optimized with respect to free energy. Learning corresponds to updating the model parameters. Here the initial states, it's just bean counting, updating Dirichlet counts. Looks very much like associative plasticity and Hebbian plasticity in the brain. And action selection is just, once I've applied my softmax function, I just choose the action that has the greatest expected value or expected free energy. And one can play games in terms of working out in which parts of the brain this might happen. But what I want to do is just briefly show you a demonstration of this in action using the simplest model possible, generative model possible. So in this generative model, we're simulating a little two-step maze task. So the idea is that this little mouse here can make two moves, and its objective is to secure its prior preferences or its rewards, which could be on the left or the right-hand side. The twist here is that there's this instructional cue, that if it uses up its first move to go and see the color of this instructional cue, this cue will tell it where the reward is. So it can guarantee getting the reward on the second move. And I should say that once it's made a move, it has to stay to one of these two arms here. These are absorbing states, and it has to stay there, which means that from the point of view of expected utility, that has the same expected utility as taking a gamble and seeing if it's on the right or the left, and then having to stay there. Half the number of times it'll enjoy being with its food on two moves or two epochs, and the other half of the time there will be no reward at all. So from the point of view of the Bellman optimality principle, both policies, all combinations of policies, or those that involve visiting the instructional cue and then the reward, or going to a putative reward location and staying there, they both have the same expected utility. But from the point of view of self-evidencing, clearly it's going to be more useful to resolve your uncertainty by going to the instructional queue and then going and getting your reward. And that's exactly what happens. So I'm just illustrating the characteristic behaviors. You get this kind of behavior, whatever example you choose. But here's one of the simpler and original examples we used to demonstrate this. So what I'm showing here is the behavior in terms of the initial state, whether the reward was on the right or the left-hand side over a sequence of trials, the action or the policy that was selected, one of 10 combinations of different moving upwards and downwards or going to the right or the left. As time goes on, the actual performance in terms of the expected utility or negative cost and the outcomes. And crucially, we equip this agent with the ability to learn the initial context from at each trial. Was the reward on the right or the left? And initially, we switched it around, but then we left the reward on the left-hand side, so that over trials, this agent learns that the reward is always on this side. So initially, it goes and does its epistemic foraging, responds to this epistemic affordance of this intrinsic value, this information gain, the value of information, and then confidently goes to secure its reward. But as time goes on, that epistemic affordance, or that intrinsic value, starts to wane. Why? Well, because it learns that the food is always over there, and there's little information value in wasting a move by going to the instructional cue, or you can read this as a conditioned stimulus. So at a certain point, there's a threshold crossing where the extrinsic value becomes greater than the intrinsic value, that is slowly reducing as the agent becomes familiar with its environment and less curious about the state of affairs, and responds less and less to the epistemic affordance of this conditioned stimulus. And at a certain point, it switches to this exploitative behavior. So what we have here is a really simple model of a deterministic transition from exploration to exploitation. That is a simple reflection of the fact that there is belief updating in the game, and at a certain point, that Bayesian optimal design of that epistemic part of the objective function is now given way to the pragmatic part that is scored by the expected utility or the expected realization of the prior preferences. So I'm going to conclude now with exactly the same story, but in a slightly more elaborate setting, where I'm going to completely ignore reward and extrinsic value and just focus on this epistemic affordance part of the expected free energy, this uncertainty resolving aspect, and seeing how far we can get in simulating something which we're very expert at, but is actually a really challenging thing, which is basically accumulating evidence from spoken or heard or read language, and abstracting meaning from that at different temporal scales. So let's just return to this formulation of the task, the problem, and its solution in terms of active inference as an inversion of a generative model. In terms, from the point of view of the graphical model and the accompanying factor graph. And now let's just ask, well, how can we make this more realistic in terms of going beyond the Markovian kind of causality and structure in a real and lived world to the kind of semi-Markovian structures we see with deeply structured causality. And it's really very simple to put this this deep structure into these generative models simply by putting one Markov decision process on top of another one, with a key twist that the transitions at the higher level unfold more slowly than the transitions at the lower level. So you can think of the higher level as basically supplying or modeling or generating a context in which the lower level unfolds or unpacks. And literally in this instance, this generative model generates occasionally a new initial state, which was the context in the previous example of was the reward on the right or the left. And given that, then we can have states at the lower level fluctuating and transiting through orbits or not to generate a sequence of outcomes at the lower level where one or other or both are informed by prior preferences via this expected free energy. So what we have here is a deep and a diachronic or generative model where we've got slow stuff going on at the top and faster stuff going on at the bottom, which generates these fast sensory samples that are all contextualized by this slower dynamic at the higher levels of the model. From the point of view of message passing, that generation, top-down generation of a context unpacks into or translates in terms of model inversion as basically using the evidence from trajectories at a lower level to inform the beliefs about the context in which I'm operating. So I'm slowly accumulating evidence in the sense that I'm updating my beliefs about a slow change in context based upon the processing of fast evidence accumulation mechanics afforded by this message passing at the lower level of the model. And here are the accompanying formal definitions of the generative model and the variational message passing that comes from this factor graph. So let me close then with integrating those brief update equations under a deep generative model that has this diachronic or deep temporal aspect. And what we've done here is try to model a very elemental kind of reading where instead of letters, we're using little icons to stand in for words. So at the lowest level, the kinds of outcomes that this agent can sample are basically letters, little icons here, a pile of seeds, a bird and a cat. It also knows where it is looking at the current word. And to generate at any one point in time, the two outcome modalities here, the two sensory inputs, if you like, I'm going to need to know the latent states, which is basically where am I looking in terms of this particular word and what is the word? So if I knew what the word was, say this composition of letters here, which we'll call flee, when there's a bird next to the cat, it has to fly away, or it can eat, or just waits if there's nothing next to it. If I knew the word and I knew where I was looking, and also I'm introducing an extra flip hidden state here, which you can think of as a change in fonts, for example, then I can generate exactly what I would see at any one time. And I can just write that down in a very simple Markov decision process, depending upon where I saccade to that changes the controllable state, which is where on this in this word I'm currently directing my gaze. But now I can equip this model with an extra level. So what would I need to know what word I am currently looking at? Well, I need to know the context supplied by the sentence from which this word came. So here in this example, there are 6 sentences that unfold as I move from one word to the next in a sentence in a particular order, depending upon which sentence I'm currently looking at. So again, I need to know where I'm looking in terms of which word I'm looking at and what sentence I'm looking at. And if I know where I'm looking and what I'm looking at, then I can tell exactly which word I'm currently scrutinizing or sampling or foraging or visually palpating, and then I can generate, given the lower level states, the actual outcomes. And I can also generate outcomes in terms of where, which page I'm looking at. So again, a very, very simple generative model. We now take the factor graph, we operationalize those belief updates, integrate the system, supplying the appropriate stimuli to this agent, who now is actively in charge of gathering the next bit of information in terms of where she looks and on this particular letter and which letter to jump to in the future. So this is sort of epistemic foraging of a pure sort that is meant to simulate the way that we scan text when reading. And indeed, the kind of behavior that emerges from this formulation is very reminiscent of the way that we actually read things, in the sense that, well, let me just show you what, describe what this is showing. What we're seeing here are a sequence, the sentence with a sequence of words that say flee, wait, feed, wait, which is the sentence that this synthetic agent was reading. And here are her saccadic eye movements. So initially, she jumps to the cat and then immediately ignores the rest of the letters in this word and jumps to the next word, simply because she knows exactly that this must be a flea. It can't be anything else. So she doesn't waste any time foraging around the rest of the letter. She goes on to the next information-rich, epistemically valuable, or uses the epistemically valuable action, which is actually jumping to the next word, and just has a couple of samples here, concluding that this is a wait word, and then jumps on to the next word and forages around until she gets the most informative and definitive evidence that this is a word, and then moves on to the next one. So this is a depiction of exactly that simulation in terms of evidence accumulation and belief updating. That's trying to illustrate the implicit separation of temporal scales under these deep generative models. So what we've done here is just plot the synthetic neural activity encoding the expectations about what is the word, the letter that I'm, or the word that I'm currently looking at, given my sampling of the letters, and what is the sentence that is generating that letter. Now, that word. So at the first level, there are only 3 words that I could possibly bring to the table to account for my sensory input. And these change depending upon which letter I'm looking at. And we see rapid changes in the beliefs. We've got flee, wait, feed, and ultimately wait. And of course, that is the sequence that is being generated by the top sentence here, flee, wait, feed, and wait. And as I am building these beliefs, optimizing these beliefs, and choosing the actions that optimize those beliefs or resolve uncertainty about those beliefs, I'm also accumulating evidence about which sentence I am actually reading. Now notice the first and the fourth sentences are only distinguished by the last word, so I can only resolve my ambivalence about whether I'm looking at these 2 sentences right at the end when I see the last word, which is indeed wait. This graph shows you exactly the same data from both levels, but we simply filtered it using bandpass filtering that you typically use in electrophysiology to generate synthetic field potentials, local field potentials, that allows us to make an observation that the Bayesian mechanics in play here generate belief updating schemes that look very much like what you see in a real brain. So for example, in terms of unit activity, you can think of these representations here, expectations, as being reflected in perisaccadic delay period activity in the prefrontal cortex. And there's a remarkable similarity between the synthetic ERPs or local field potentials and perisaccadic field potentials during active vision in sort of lower and higher levels of the visual hierarchy here, speaking to a certain neural plausibility, at least at this coarse grain level of analysis, of the kind of message passing that is implied by these this generative model. So that's the story. I'm going to give the last word to Einstein in terms of making things simple, just to emphasize that all that epistemics, all that explorative and information seeking behavior is basically acting in a way to maximize the expected simplicity and resolve uncertainty that becomes part of this this imperative to maximize expected model evidence, or it's bound in terms of an elbow or variational free energy. So it just remains for me to thank those people whose ideas I've been talking about. And of course, thank you very much for your attention. Thank you.
Thank you, Karl, for a very exciting presentation. We have now some time to take questions from the audience. I know there are some questions on the question and answers.
Yes, let's start with the Q&A first, and then we have some in the chat as well, but we'll start, well, I think we have some may have been answered, but we'll start with the Q&A first. So Shreya, we can read it out and then we can go from there.
All right. There's a question from Kripa Rajshekhar. It says, how does the free energy principle FAP relate to a cybernetic analysis of systems, in particular those with symbolic language use? For instance, why do biological systems with language or culture consume so much more energy than those without? For example, the famous anthropologist Leslie White noted, culture evolves as the amount of the energy harnessed per capita per year is increased, or as the efficiency of the instrumental means of putting the energy to work is increased.
That's an excellent, if wide-ranging question, which allows me to sort of just pick up on some sort of key points that are implicit in this question. You know, first of all, the question, how does it relate to cybernetic analysis? Extremely closely. So this notion of a generative model that's trying to secure evidence for itself is very, very closely, in fact, one could read it as a sort of 21st century version of the good regulator theorem from Ross Ashby and colleagues. So one of the fathers of cybernetics, where the theorem, which he considered provable, is that if you've got any regulator, any subsystem in a larger system in which it is immersed, namely its environment, any system that can control or regulate its environment successfully must be a model of that environment. And that's exactly the same assumption in this formulation of active inference, in that I am a generative model of my lived world. And that all I have to do is to optimize my model to make it fit for purpose, to explain and account for my my model. The second point, so I should say, of course, that sort of notion of the good regulator theorem and cybernetics is not so distant from sort of notions of self-assembly in computational chemistry, or indeed autopoiesis in the life sciences, which again I would say that the formalism that I've been talking about can be regarded as a mathematical statement of these notions. The next set of questions are more about the consumption of energy and symbolic languages. I think those speak to some really key points that are unified by this drive to simplicity, the minimization of complexity. And I remember talking earlier this afternoon about the importance of eluding sharp minima and trying to find those global flat minima that have this maximum entropy, this maximum curvature aspect, this this closely related to Occam's principle. So the minimization of complexity. What's the best way of making your explanation for the world, your generative model, as simple as possible? You coarse grain. So how are you going to coarse grain a very high dimensional continuous state space out there, latent states generating your sensory impressions? Well, one of the simplest ways is just to coarse grain it into a discrete state space model. So from my perspective, having language and symbols is just a way of saying that perhaps it's more appropriate to have discrete state space models, sort of epsilon machines, hidden Markov models, Markov decision processes, whatever you want, generating sequences of data because they have the right level of complexity. And then the question comes, well, how coarse-grained do you want your states to be? How many states are there? How many words are there? What kind of Lie algebra do you want? Do you want to reduce your description to? So I would look at the emergence of symbolic language use, ignoring all the cultural evolutionary psychology arguments that you can also frame in terms of Bayesian model selection, natural selection, but ignoring that and just focusing on the simplicity that is afforded by coarse grading and categorizing, having symbols that stand in for, in the semiotic sense, what would otherwise be a rather complex game to try and model accurately. So if it's simpler to use a language or a set of symbols or coarse graining, why does it cost so much energy when I've just said that complexity scores the energy cost by Landau's principle? Well, I think the answer to that is, remember, the evidence is the difference between accuracy and complexity. So if you're if you're compelled to maximize your evidence, you're compelled to maximize the accuracy, but keep the complexity as low as possible. But the complexity is always chasing the accuracy. So there will be a natural tendency in any system that is adaptive and accumulates information and whose generative model becomes more and more apt to explain its sensory exchanges. There will be a necessary complexity cost that is more than licensed by the increase in the accuracy until a certain point where you don't go any higher. Otherwise, you start to overfit and fail to generalize. So I think that you see the careful and discriminate use of energy in an evolutionary context as really a reflection of the growing complexity of the generative models in possibly our self-assembled or niche constructed and encultured worlds that is fully licensed by an increase in accuracy. Everything is now more predictable and we are better at predicting it. That is especially true of language. There is just a reflection of this tendency to maximize marginal likelihood or model evidence. That's my answer.
Professor, there's another question. Should I read it out?
Yes, of course. So I can read it as well, so I'm cheating to a certain extent.
Okay. So the question is, in the fractal graph, should there be a cycle between G, the goal of the policy to minimize surprise, and D, the model being trained, or bean counting, that I think is used to P, then S_D, the agent generate its own data to minimize surprise and then trains the model to model the world and its belief properly?
Right, I haven't read that one. That sounds a very sophisticated question. So if I do remember properly, the question here is in this sort of message passing factor graph formulation, should the G be connected to the outside? And yeah, that's absolutely right. So if you remember when we had this graphic talking about the action perception cycle, and I was emphasizing the circular causality that is mediated by the external states, that is certainly a really important aspect of this kind of belief updating, where your beliefs about what to do next determine the actual action upon real states of the world that generate the data. So that now you've got this curious, again, almost autopoietic aspect to inference, hence active inference, where your inferences determine the data that you're making inferences about. And of course, you're leveraging that sort of confirmation bias and circularity in keeping yourself sampling the kind of data that you want to sample. So there's an inherent, if you like, confirmation bias and optimism bias that's written into this kind of circular mechanics. That just is the description of self-organization to a particular set of outcomes, and implicitly a particular set of states that generate those outcomes. So I hope that was the spirit of the question, but I can't actually read it. So I don't know if the person who was asking the question is present, or whether you have to ask them if that was a satisfactory. Is there something that breaks us out of this cycle? Oh, that's an interesting question. Shall I answer that question? I can see that popping up on my screen, so I'm not sure I'm allowed to just answer ad hoc questions.
Yes, go ahead. I think there's a 2 follow-up from Glenn. Is there something that breaks us out of this cycle, and so we know we can get a perfect model?
Yeah, I mean, there's no such thing as the perfect model, in the sense that, what I haven't spoken about today are the different levels of optimizing, extremizing this free energy functional. So it can be, we look briefly at learning when we're looking at the example of learning the synthetic rat learning the context in an environment with which she was becoming familiar. But a more important aspect, so an equally important aspect, is the structure of the generative model itself, in terms of which connections, contingencies, how many levels in a hierarchical model, how many factors do you introduce, and this kind of Bayesian model selection, which is just another free energy optimizing process, or maximum marginal likelihood optimizing process, is known in the work of people like Josh Tenenbaum as structural learning. And I've recently learned that comes from the field of radical constructivism. But exactly the same problem exists, or not problem, but exactly the same optimization process emerges from this treatment of sentient behavior, so that your model itself is always being optimized, either at an evolutionary timescale, so that on that reading, natural selection becomes nature's way of doing Bayesian model selection by extremizing an fitness function, which in this instance would be a variational free energy. The point being that there is never a perfect model, and that you ask yourself, a model of what? Well, of the data that's being generated. Well, but if you're in charge of your data, how do you ever know what the perfect model is? Of course, the perfect model is just in a sense, when the environment supplies exactly what you predicted, and you minimize your complexity, and everything unfolds according to your prior beliefs. But of course, in reality, you're dealing with a capricious changing environment, simply because our environment is built of or comprises lots of creatures like us. So we're always chasing, if you like, the structure and the parameterization and the states under a best model, where best is just operationally defined in terms of the marginal likelihood given some data. So that's how. So you get to a perfect model, given that a perfect model doesn't exist, simply by learning and doing your structural learning, or learning in terms of model parameters, so say experience-dependent plasticity, neurodevelopmental learning, and Bayesian model selection, again at a neurodevelopmental level or an evolutionary level, in the service of maximizing model evidence.
Professor, there's a related question. It says, can you discuss how cognitive conflicts relates to breaking out of the cycle, and when is it optimal to engage in it versus not?
Yeah, that's an excellent question. It sort of brings to mind some notions of cognitive dissonance and the like. Yeah, I think it's informative. I mean, I'm not going to answer that question, but certainly it's a great question. And you start to ask, well, how would you simulate that in silico? How would you actually sort of simulate a Bayes optimal agent who's in a state of crisis or existential angst or cognitive dissonance? And the way that that normally works is that you're contended. You set up a situation where all the sensory evidence at hand speaks to a very low confidence way forward. So we're now talking about the beliefs about different policies or choices or plans. This is more simply plans. If it's the case that the two or more plans are equally likely, then the precision of your beliefs over pi or your plans now have a very high entropy, and that's usually associated with a kind of dissonance, a kind of angst, and indeed a negative valence that now can be, if you like, registering a state of conflict in the limited sense that there are now conflicting ways forward that are equally attractive in the sense that you are assigning an equal posterior probability weight to. And interestingly, if you work out how you would optimize the hyperparameter contouring the precision or the entropy of those beliefs, and do so in terms of a sort of Gibbs distribution, it looks as if dopamine has all the characteristics that is in the game of registering when you're in this state of dissonance or uncertainty about what to do next. And when you resolve that, and when you know exactly what you're going to do next and commit to a particular plan of action very confidently, then the precision of those beliefs increases and the hyperparameter encoding that precision increases. And if you simulate it, it looks very much like sort of a phasic dopamine response. So if the question was about how do you understand dissonance and conflict in this sort of active inference world, it is really about put simply, it's really the uncertainty that requires you to select among a number of equally plausible hypotheses or models or explanations. And in particular, when those hypotheses are beliefs about how you're going to act, that can have a very personal and agential aspect to it that people normally associate with, I repeat, with anxiety and angst. So is that a reasonable answer? Is that what the questioner was getting at, do you think? I'm not sure.
Professor, there's another question. It's from a Turing Award winner. He's Joshua Bengio, and I'm going to read his question now. How to make the difference between epistemic uncertainty and aleatoric uncertainty, which are both included in the surprise in information gathering policies?
Right, could you just repeat the two technical phrases?
The epistemic uncertainty and the aleatoric uncertainty.
You're going to have to ask him I've heard that before, but you're going to have to ask him if you can put it in a slightly simpler phraseology for me.
Right, maybe we can unmute Joshua so that he can ask him his question.
Yeah, I can do that. I'll do that right now. 1 second.
Hey, so aleatoric uncertainty is just noise. It's the uncertainty in the world that no matter how much you acquire information, you will not be able to resolve. So if you are trying to just maximize the amount of surprise in your quest for information, you might go to places that have a lot of noise, whereas really you only care about the epistemic uncertainty, which is the reducible part of the unpredictability.
Perfect, thank you. So I should have known that. I have been taught that before. I just forgot it. Yeah, so that unpacks in this decomposition of this expected variational bound or expected free energy in terms of the pure epistemic part that is the reducible uncertainty. So that's scored by the anticipated or the expected information gain scored by the KL divergence between a posterior and a prior. The I can't pronounce it, but the noisy bit is there, but requires you to rearrange the terms, and that would be basically the ambiguity, which may be irresolvable. So the noisy bit is usually written in terms in these discrete state-space models into the likelihood function. So it's the precision of the likelihood mapping, so that in a very dark room or in a very noisy context, all outcomes become equally likely for any given cause. So in the decomposition that I was walking through in the presentation, I would assign the noisy bit to the ambiguity, which you're trying to minimize, and the epistemic uncertainty to the intrinsic value, which is the reducible part, of it. So when you put it all together, it looks as if the agents are selecting those policies that are going to be optimal in reducing the reducible uncertainty, the epistemic uncertainty, while avoiding states of being that have very noisy likelihood mappings, so that you will, in the absence of any epistemic value, you will be basically searching under the lamppost, so that you're avoiding noisy or dark or uninformative or ambiguous scenarios. I mean, one simple manifestation of that is that it's an example that usually comes out in the context of what's called the dark room problem in philosophy. If you want to minimize surprise, why don't you just go to a dark room, switch the lights off, and stay there quietly? Then you're not going to be nothing. You don't expect anything to happen, and therefore your surprise is minimized. So it is exactly this imperative to minimize expected surprise, by which I mean minimize uncertainty, which, if you like, dissolves the dark room problem, because the first thing you do, an epistemic agent does when she goes into a room, is to switch the light on to make sure that she doesn't bump into things. So those two aspects of the different reducible and irreducible uncertainties are absolutely crucial in shaping the right kind of behavior under this formalism. Is that the kind of, I dare say, the alloretic noise that you're talking about?
Yeah, so there's an issue with aleatoric uncertainty and noise. If I understand well, you're saying it's going to be captured by some parameters of my model, like Gaussian variance or something like this, and that's going to allow us to factor the epistemic reducible part of the uncertainty. But the problem is, when an agent is building its model of the world based on finite amount of data, so in the limit, what you say works. But in general, if you want, there's going to be overfitting, right? So we're going to underestimate how badly we will predict in the future because of that. And so it makes it difficult to disentangle epistemic and aleatoric or noise.
Yep, I mean, a great question, which sort of speaks to two key points. So you're absolutely right that in all of these instances, realizations, demos of this kind of active inference, there is an implicit estimation of this kind of noise. So in when you're dealing with continuous state space models, they'd be normally cast, or at least the inference part would be normally cast as a Bayesian filter, an extended Bayesian filter, and the noise estimation part would be the Kalman gain. So inevitably in these schemes, you have to optimize the hyperparameters that underwrite the Kalman gain. When you look at what that would manifest as in a sort of neuronal network setting, it looks very much like attention. So that, by optimizing the precision of likelihood mappings under continuous state space models during a Bayesian filter, that looks very much like what the brain does in terms of affording more attentional gain or weight to certain sensory inputs that it believes have a greater precision and thereby endow them with the ability to induce belief updating higher in, say, a cortical hierarchy. In discrete state-space models, it is literally, as you say, the precision of the likelihood mapping, usually written down as a Dirichlet process, and that can be now conditioned upon different contexts. So moving on to the second part of your problem, you're saying, yes, it is very difficult to do that. It is very difficult to do that, but it has to be done, and it is done. You know, I am my own existence proof and all that. And the way that that is normally done is by now having a model space in which you condition the precision of your likelihood model on a context where the context is inferred at an appropriate level in a hierarchical model. So you write in the attentional sampling, as it were, into the generative model, and then you optimize that just by belief updating in the normal way, or in this instance, you would be sort of learning in the normal way, learning the Dirichlet parameters that describe this. In respect to your natural question, yeah, but surely this is an impossible problem at the beginning because of the problem of overfitting. No, I think it's important to sort of push back on that. The whole point of using a variational or elbow function, it is equipped with a complexity penalty, which precludes overfitting. In principle, it can't overfit. So I don't think it's the overfitting which is the problem. I think the real problem, which you may have been speaking to, is actually testing the universe of models that you could bring to the table to properly accommodate the conditioning of, say, the precisions of various mappings, for example, on different kinds of context, and that, you know, I think that is an unsolved problem. But clearly, again, because you and I are here, some artifacts have solved that problem, and I put that under in the problem domain of structure learning. You know, finding out the right generative models that can recognize the right context they're in, and then deploy the right precisions to optimally sample the right kind of data or ignore other kind of data. And I use ignore here in the psychological sense as the complement of applying attentional selection to one subspace of data space or another space. Is that what you meant by the difficulty of doing this before you know the nature of the generative model?
So I mean, the overfitting part is due to in a finite data set, learners tend to. You're saying there's no overfitting if you're Bayesian. I just don't believe it, and the reason is you don't have a perfect prior. You may have like wrong assumptions, so there's like bias, and that's not going to be accounted for in your Bayesian variance. So there's going to be a gap between what you think is how well you're doing, and you're going to overestimate how good you are in your predictions.
Yep. Okay. Well, so two really important points there. First of all, because we deal with hierarchical generative models, there is no one prior. So all the heavy lifting is done by the intermediate levels in a hierarchical generative model. So they're empirical priors. So they are updated and they are learnable. So they're learnable or trainable priors. So there is no wrong prior in these hierarchical models. But if there was, and I think there is, if you allow me to assign the structure of the model the label of prior. So if I bring a particular structure, say I brought a VAE or a GAN to the table, and it had, say, 6 levels, and it did or did not have some recurrent connectivity and all the architectural aspects. If you allowed me to call that a prior, then I think I can see your point is that if you start off with the wrong structure, then you're not going to be able to optimize the marginal likelihood of the model evidence. But so what does that mean? Well, it means you have to put structure learning into the game. You have to explore different structures, and that's what I was talking before about Bayesian model selection in terms of the structure selection, which brings us back to the problem now of exploring the space of different structures. But there are solutions to that which are used in statistics, but not in machine learning. And I'm thinking of things like Bayesian model reduction. So if you know the functional form of your posteriors and your priors, and you make the conceptual link between a prior and a model, then you can do your model selection and structure learning, basically prior learning, by framing it in terms of different priors you could bring to the table. And there are procedures that actually allow you to score thousands of different structures or models or priors on the basis of inversion under a full model. So I think there are really interesting ways forward from the point of view that the low dimensional kinds of generative models that we deal with, which I suspect from your perspective would be regarded as sort of toy models or demonstration models. The other issue I think is important just to acknowledge, which is this overconfidence issue. You're absolutely right, that sort of variational inference, because you're assuming a particular functional form for your posteriors, is typically characterized by an overconfidence problem, and that certainly has to be offset or accounted for when doing sort of variational inference and variational learning. So that is an issue, usually again resolved by structure learning, by having sort of slightly less coarse-grained approximate posteriors to resolve that.
Thank you for your answers.
Dr. Friston, we'll be taking 2 more questions, after which we'll be finishing. So the first question is this thermodynamic model of the brain related to Jeremy England's dissipation-driven adaptation? And if so, how? How is our policy selection process a microcosm of our evolutionary history?
Right. Again, very challenging questions and informed questions. So at one level, there is no connection between a variational free energy and the thermodynamic free energy of the sort that Jeremy England is dealing with. The phrase free energy just inherits from the functional form of the objective functions. However, there are in physical systems, and particularly thermodynamic ensemble systems, you can certainly see the same kind of self-organization, free energy minimizing behavior when you read those functionals as a thermodynamic free energy. And the kind of problems that Jeremy England is dealing with is sort of a similar problem, but using a very different kind of mechanics in terms of thermodynamic free energies, where he's trying to understand the emergence of self-organization and how you pay the energetic costs of energy production that is normally associated with dissipative systems that maintain themselves in some kind of non-equilibrium steady state. The free energy that I'm talking about is a little bit distinct, in fact, very distinct from that. It's purely an information theory and does rest upon having a separation between the states that are encoding the beliefs and the things that one has beliefs about. So you have to have a distinction between internal and external states, and it is in that distinction that the free energy that I'm talking about emerges. However, having said that, they're both trying to understand what are the properties of self-organized states that have some steady state aspect, that have some enduring aspect, either from the point of view of a physicist, thermodynamics and non-equilibrium steady states, or from the point of view of a dynamicist and information theorist. How do you keep inside your attracting set in some set space, some state space? And the second bit of the question was can you remind me?
Yes, Professor, just 1 second. It was, how is our policy selection process a microcosm of our evolutionary history?
Well, I think, again, a great question, and we've already mentioned that to a certain extent. So the process, policy selection is just an act of Bayesian model selection. What is Bayesian model selection? Well, it's just taking a number of structures or a number of models or hypotheses, scoring them in terms of their marginal likelihood or evidence, or an evidence bound such as variation free energy, and then just selecting the one with the most evidence. So that's how policy selection works in the simulations that I showed you. And that's how Bayesian model selection works in model comparison and statistics and refining the structure of various models. And there are many people who now think, particularly those who subscribe to sort of universal Darwinism, and people who have a Bayesian filtering take on things like replicated dynamics in theoretical biology. There are people who think that natural selection is just this process. It's just the process of implementing Bayesian model selection over evolutionary timescale. And it's an interesting game to work out, well, what's the hypothesis and what's the evidence? And if you sort of think through it, it usually transpires that basically the model becomes the phenotype. And the hypothesis is, evolution's hypothesis is this phenotype a good fit for me, the environment? And then I'm going to select those that have the greatest marginal likelihood, the greatest model evidence. What would that look like? Well, it would simply mean that those things that are more likely to exist in the sense of they are characterized by this set of exchanges with the environment, their observations of their outcomes, are going to be retained. So it has that tautology that natural selection has, but nicely now articulated in terms of natural selection operating to maximize an objective function. So it's putting a teleology on natural selection, where the teleology could be written down as a free energy function. And people have done that. People like, I think, Stephen Frank have shown that under simplifying assumptions, replicated dynamics is just a Bayesian Kalman filter. There are other people who take a slightly more heuristic approach from the point of view of universal Darwinism, and again sort of celebrate the sort of the implicit tautology by associating adaptive fitness with just this evidence that I exist, which is the model evidence.
Thank you so much. Dr. Friston, I'm going to read out the last question for you. It says, does language also not create novel world possibilities through a mechanism like the adjacent possible, as suggested by Stuart Kaufman, perhaps prompting a positive feedback loop that makes the notion of accuracy or control impossible, not to mention necessitating probability measures on expanding spaces, sampling a species problem?
Right. I'm not going to provide a very convincing answer to that question. And I also noticed a little follow-on question. Am I assuming that evolution is the only selection process? Absolutely not. In fact, the converse. That you get this selective process everywhere at all sorts of timescales. And I'm also mindful of one of my mentors, Jerry Edelman, bringing neuronal group selection to the table as an instance of this selective process as well. So you see this in neurodevelopment. You see this. You can see the selection of non-redundant synapses during sleep in terms of the synaptic homeostasis hypothesis of Giulio Tononi, which can be cast as a complexity minimizing device that does a kind of structure learning every day. So it's not just natural selection and evolution I was talking about. Any selective process based upon marginal likelihood can be put on in that camp. The question about the uncountable infinity or sort of finite infinity of language, was that the question? And does that not make everything unpredictable? Was that the spirit of the question? I'll ask the chairperson to see whether I've got that correct or not.
Should I unmute the speaker? 1 second. Give me one second.
Yes.
Hello, can you hear me?
Yes, I can, yeah.
Oh, thank you very much. Your answers have been very helpful. And I think it's what you were saying, but maybe less sophisticated in terms of, my understanding of the adjacent possible is that you invent a word, and that word, let's say a blockchain or Bitcoin, then creates possibilities for a certain set of actions that could then create yet new possibilities that would previously be impossible. And that because of this expanding space, you have the notion of positive feedback. And it connects to the whole energy issue, which is, can we really, in the context of positive feedback, is the notion of control, when you have that type of singularity, does this all sort of just become more or less impossible, and we need new tools in that situation? And language being an example.
Yeah, I mean, it's a great example. One of the great challenges in terms of getting proper natural language understanding under the hood in sort of machine learning. And a great question. I think there's a practical answer to that question is that certainly in the sense of, I came across this notion of diagonal operators in computation theory and the replication that ensues from that. The way that that doesn't offer a problem from the point of view of building a good generative model to understand, say, language, is again, it's this simple imperative to keep things simple. So every time you induce another another level or layer or composition or sequence of a sequence of a sequence, or sort of hash code or zip codes of zip codes, every time you do that, you're introducing more degrees of freedom. So you can only do that if by introducing those extra degrees of freedom, you more than pay the price in terms of increasing the accuracy. And of course, at some point, the predictability of the thing you're trying to supply an accurate explanation for will make that impossible. So you're going to go up to as complex as possible, but at some point going any further, you're going to start to have an overly expressive generative model that is going to not generalize, it's going to overfit, and therefore, if you've got the right complexity penalty in play, it'll start to simplify itself again. So from the perspective, the infinite possibilities and combinatorics that is afforded by things like language is not a problem from the point of view of trying to understand how this person or how this culture is generating language. And indeed, one can then sort of tell very simple arguments where you can understand this variational treatment of self-organization in terms of just making the world more and more predictable. How do you do that? Well, you learn to speak the same language as your conspecifics. And indeed, you learn to speak the same language as your environment, and you start to build your environment so it supplies unambiguous, simple things that you predict, like edges that you predict by by edge detectors in V1. But language, I think, is the most beautiful example of this. It just enables us to predict each other. So the question about tools, then, well, so what about this beautiful mathematical recursive aspect that in principle means you could go out there into hyperspace with various operators or functions or representations or graphical models or stick breaking processes. I think that kind of maths and that kind of, if you like, expressivity may be, I don't know how, but it may be the solution, the tool that solves what we were talking about with the previous challenging questions about sort of the structure learning, exploring the space of models. It may be that having that kind of calculus at hand allows you in a reasonably structured way to explore extensions to your generative model. And if you can do that, then we already have the mechanics to score this new one. And if it passes the marks, the evidence increases or the free energy increases, then we retain it. If not, we revert back again. So it may be, I'm not quite sure what kind of calculus or computational theory you had in mind, but if it is of the sort that brings new, more complicated architectures to the table, or mappings to the table, or functions to the table, then in a principled way, then it might hold the key to how we explore model spaces and do structural learning. And I think that's again, it comes back to the earlier question that we were wrestling with in terms of avoiding overfitting and getting the right conditioning on context and the like.
Thank you.
Is that the kind of calculus? Is that what you had in mind?
Well, we're working in the area of innovation, and there's like a variant of the Polya-Earn sort of sampling method, which is related to the Dirichlet process, but you want to actually have some notion of a possibility that then colors the types of future possibilities that might become possible. Again, I'm using possible too much, but you know what I'm saying.
I think so. Well, I probably don't actually. I probably
but thank you very much for your answer, though.
But I mean, certainly your hierarchical Dirichlet processes, I think, a really nice example in terms of how far do you want to go in extending them. Of course, that's the problem that people in non-parametric Bayes are trying to resolve, and it may be really important to solve that to get sort of natural language processing as fluent as it can be.
Thank you.
Thank you.
Thanks a lot, Karl, for a very exciting talk. Thank you so much, everybody, for questions. I hope we managed to cover most of the questions, if not, well, at least these questions that we had on the question and answers, as well as chat. Again, thank you so much, Karl, for staying with us so late, because we are on different continents. And we do hope to see you in person in New York sometime soon.
Well, thank you very much. It's an honor to speak to you. It really was a pleasure. And some great questions. I'm going to have to go away. I'm going to have a cigarette and think about them and see if I could have thought of better answers.
Thanks so much. Thank you so much once again. Thanks, everybody. Thank you so much, Karl.
Bye-bye.
Bye.